Hello everyone, my name is Ujjwal and today I'll be talking to you about remote sensing. This is a topic that is really close to my heart because this is how I ended up in the geospatial industry. I first learned of remote sensing about 20 years back. I was this young undergraduate engineering student who had no idea about remote sensing. But I got an internship at this place called Indian Institute of Remote Sensing. When I ended up there and started working, I realized this whole world of remote sensing that existed, which I never knew before. The satellites, the sensors, the technology, the techniques for image processing were unlike anything I've seen before. And for me, the biggest reason I love remote sensing is that it gives you this unique perspective and the ability to see the world in a different way and solve interesting problems that you can't do otherwise. So in this video, I'll try to share some of the magic of remote sensing with you. If you're not from a remote sensing background, you will learn about the terminology and the techniques that are used in remote sensing, and then you'll be ready to start using a software like Google Earth Engine to apply those techniques. If you're already using remote sensing, this talk also contains some tips and tricks and practical insights that will help you work with this data better. And also, we are talking about a whole range of sensors. So if you are familiar with a certain kind of satellites and sensors, you might learn about other data sets that might help you solve a problem. Also, I believe that the best way to learn remote sensing is just to look at data. So this talk is almost entirely pictures. So rather than looking at me talking like this, you will get to see all the pictures and learn about remote sensing. So let's get started. Remote sensing is a very wide field. So in this talk, I'll focus on the satellite imagery and particularly the public domain satellite imagery. The first thing you need to know is, how do satellites see the world? What do they see? How do they measure the world? How do they capture the data? This is how satellites see the world. They look at the Earth as through the light that is reflected from the sun. So the sun emits a lot of radiation in form of sunlight. That sunlight reaches Earth, passes through the atmosphere, hits the Earth's surface, and some of it gets absorbed, some of it gets reflected. And the reflected light travels back through the atmosphere and through the space where the satellites are up there measuring that. And that is what the satellites see, the sunlight as it is reflected from the Earth's surface. And this kind of sensing is known as passive remote sensing, that it's just looking at the light that is reflected from the Earth. The sun's light is actually a form of electromagnetic radiation. It consists of radiation in many different wavelengths, and our human eyes are sensitive to only a small portion of it. As you can see here, this is the visible spectrum. This is what human eyes can perceive, the light from blue to red. But you can see there are other forms of radiation that is part of the sunlight. You might have heard of gamma rays, X-rays, ultraviolet, and so on and so forth. And what remote sensing allows you to do is we can have a sensor that is sensitive to different parts of the electromagnetic spectrum, and you can measure how the light is reflected in those wavelengths. So the important concept here is to remember that there are many different wavelengths ranging from very small to very large, and you can design a sensor that can look at a particular set of wavelength and measure the reflected light in that particular wavelength. And these are called different bands. So let's look at the data from a satellite, and we can then learn how the world appears in these different wavelengths. So this is a satellite called Landsat 8. It's the eighth satellite in a long series of satellites called Landsat. This is a program by NASA that has been observing Earth for a very long time, since the 1970s. And this is the latest satellite that's up in the space and capturing data. This satellite has sensors from the visible spectrum and also the infrared spectrum. So let's just zoom into this part of the spectrum. And you can see here we are looking at the 400 nanometers to 13,000 nanometers. And this is the visible spectrum, the blue, green, and red bands. But we also have bands in other wavelengths, which the satellite is able to capture. So up here, these are all the different bands that the Landsat 8 satellite is capturing. And there are instruments aboard the satellite that are measuring the reflected wavelengths into this particular segments. And you can see there are the gray part here. These are the amount of light that is reflected in that particular wavelength. You can see there are certain wavelengths which gets completely absorbed by the atmosphere. So these are also known as the atmospheric windows. And you put a band that in that window, and you are able to look at the light that is reflected from the Earth's surface to the satellite. And the Landsat has many, many different bands. They range from 1 through 11. And we'll look at how the world looks in each of these different bands. You can see here there's a band here in a part of the spectrum where all the light gets absorbed. So why it is there, that's a surprise. We'll look at the data and I'll tell you all about it. So let's look at the world. This is what the world looks like to us. And this is a high resolution satellite imagery for Bangalore. And you can see I selected this image because it shows you many different kind of land surfaces. There's water here. There is some bare earth here. There's vegetation cover here. And there's some built up area here. And we'll see the same area and how it appears to the Landsat sensors. First up is the first band. That band is called the coastal band. And that band is specifically used to study the coastal regions. The reason is that the water absorbs most of the sun's light and that appears quite dark. So if you're studying oceans and ocean water, you basically see everything as the same color because everything gets absorbed. So this band is also called an ultra blue, which is before the blue band, and which helps you identify different shades of blue in shallow water. So primarily used for coastal studies. Now let's look at this blue band. And this is what the world looks like if you just look at light that is reflected in the blue band. And you might ask, why is this not blue? Because whatever the satellite measures is just the amount of light that is reflected in that band. And it just measures everything in levels. So what you see as white is the more light gets reflected, the whiter the pixel. The more light gets absorbed, the darker the pixel. So when the satellite is looking at the world, it's just measuring how much is the light that's coming through from that particular surface. And if you look at the water, that absorbs most of the blue light, and that's why it's dark. Whereas, this surface reflects a lot of the blue light, and that's why it appears bright in the blue band. Similarly, this is how the world looks in green and red band. And our eyes also kind of get the same signals in those bands. And our brain composes these 3 different bands information into an image that we are used to seeing as a red, green, and blue image. Things start get interesting when we move to the infrared band. So the 5th band in the Landsat satellite is called near infrared. And you can suddenly see the world appears very differently. If you put on an infrared goggles and look at the world, this is what you would see. The water appears very dark because it absorbs a lot of infrared light. The vegetation appears quite bright because the vegetation actually reflects a lot of the infrared light. We can't see it, but the sensors can see that and measure that. So the same world, what we saw here, looks like this in infrared. And we can use this information to do some really interesting analysis. Then we move on to another band. These are called shortwave infrared. These bands are very useful for detecting built-up areas. As you can see, the built-up areas appear quite bright because they reflect a lot of this radiation in this shortwave infrared band. Then we come to this panchromatic band. This is also quite an interesting band. And this is what a black and white photo looks like. Panchromatic, the word means pan is across, chromatic means the visible spectrum. And if you look at the diagram at the beginning of the presentation, the band 8 spans the full range of visible spectrum. And that means it's got a much wider band that it's looking at, and it's capturing how the world looks in that band. And that means you are able to see the world in a you are able to resolve things much more effectively. And this is called a signal to noise ratio. When you have a wider band, you can actually have a much better signal to noise ratio. And that's why generally in the satellite sensors, the panchromatic bands have a higher resolution. And that's why this panchromatic band or the black and white band appears at a higher resolution than the rest of the bands there. Now we come to this band called Cirrus, band 9. Remember the band I told you that's in the part where all the light gets absorbed. So why would we have a band there? So imagine we are looking at the world through the satellite, and most of the light gets reflected in this band, gets absorbed. But there are some clouds which are called cirrus clouds, which are high up in the atmosphere. And if there was a cloud there, we wouldn't know, because the other bands wouldn't be able to detect that. But the cirrus band, when we look at this light in the cirrus band, the clouds actually are able to reflect that light. And if there was a cloud, this band would appear bright in those areas. And then we would be able to detect and remove those clouds. Even here, you can see a slight variation here, and that would be the light that is reflected by this high atmospheric clouds. So band 9 is not used for any analysis, but to remove and detect cirrus clouds. Now we are looking at the thermal infrared band. So we are moving up the wavelengths, and this is the infrared band which can detect temperatures. With COVID, all of you might have seen the thermal infrared thermometers, which you can measure the temperature of a person from far away. And this is the same sensor that's up in the Landsat satellite, which is measuring the temperature of the surface of the Earth. And you can see this world looks very different. There are certain areas which are very bright, which are very hot, and other areas which are very dark, which are cool. And if we compare it with the image, you can see the bare Earth is very bright. The water and the vegetation areas are quite cool. And this gives you a very unique perspective. And this band information is quite useful in doing urban studies. You can actually detect urban heat island effect and measure the surface temperature of different type of land surfaces. And there are 2 thermal infrared bands in Landsat satellite. So we learned about how the world appears very differently. We can use this information in a very interesting way. Now let's look at the data from another satellite. This is called Sentinel-1. This is operated by European Space Agency. And this is a different satellite because it doesn't measure the sunlight that is reflected from the sun, but it actually has its own emitter, which emits microwave radiation, and it measures the amount of radiation that comes back. So since the satellite is emitting electromagnetic radiation, this type of remote sensing is known as active remote sensing. And what it does, it's looking at this particular part of the electromagnetic spectrum. This is the microwave part of the spectrum, and it transmits this radar pulses at the Earth's surface and measures what comes back. And you can kind of get interesting information based on that. So back to this area, this is how we see the area. But if you look at how does the Sentinel-1 see this area, this is what it looks. And you can see this shows you the water is dark because when you transmit a pulse there, most of it gets reflected away and very little comes back. So the signal is very less there, and that's why it's dark. Whereas this other areas where there is a structured information, whatever there is, surface is not smooth, that reflects part of the signal back, and that's what the satellite measures. Sentinel-1 satellite is really useful because it can penetrate clouds and is very useful for flood detection, because a lot of times after heavy rainfall, there are so many clouds, you can't detect what's on the surface. But through this satellite, you can detect water, open water and vegetated water, which is there on the ground and can help you detect floods. And there are different polarization. We'll talk later in the course about this 2 different polarization, but this is the information that is captured in a different way through the satellite. This is another interesting satellite. This is also a European Space Agency satellite called Sentinel-5P. And this satellite measures the radiation in this spectrum, ultraviolet and infrared. And you might think, what does it measure with ultraviolet? Because ultraviolet rays are actually absorbed by our atmosphere. And thankfully, because they are very harmful to humans and very little of it reaches the Earth. So what this satellite is measuring is a combination of the reflectors in different wavelengths, and it's used for detecting pollutants. So it's detecting the concentration of these different pollutants high up in the atmosphere using these different channels. And this is a really useful thing to learn about if you're studying pollution, air quality. This gives you really useful information. And this is a really good example of that. This is a place in northern India. And if you just look at the place, there's nothing interesting about it. But if I take the image that was captured by the satellite Sentinel-5P of the NO2 concentrations. I see there's a big white spot here. And that means there's something going on here where there's a high amount of pollution. And if you just zoom in there and you'll see, yes, there is a large cement plant. And that's emitting a lot of nitrogen oxide. And that's what the satellite is measuring. So this is what I love about remote sensing, where you can see things which are not visible to anybody else. But now you can actually look at this data and detect the source of pollutants. Next, I want to talk about processing levels. The data, as it's captured by the satellite, it goes through a long processing cycle before it becomes usable to you. So we'll talk about the different terminology that's used along the way. So you might hear this terminology, this data is level 1 or level 2. What does it mean? So level 0 is actually the data as it's captured by the sensor. So whatever the sensor measures, and this is measuring the light that is reflected from the Earth's surface as it's reached the sensor, it's measuring that. And this is the raw values. And these are also called the radiance values, which is how bright that pixel is. And that's what is measured by the satellite, and you get this data. This data is not useful unless you are really trying to calibrate the sensor or looking at the sensor itself. For application purpose, you generally don't use level 0 data. The next level in the processing is level 1. And this level applies a certain type of corrections that makes the data more usable. So you take the raw data that is measured at the sensor and you convert it to a value that is measurable. So you take the amount of light that the sensor saw and convert it to a value that is the amount of light that is reflected from the surface. Or if you're measuring, say, a thermal infrared band, it would convert to the temperature that was measured on the surface. So this is where your data becomes usable, interpretable, and you also apply this thing called geometric corrections. As the satellite is capturing the Earth is moving. By the time the satellite finished scanning the entire area, the Earth had moved. And this level of processing corrects for that and gives you a geometry that is correct. This is also referred as a top of atmosphere product, because your satellite is in the space, so the light has to travel through the atmosphere before it reaches the satellite, and that's what you're measuring. But what you're really after is what was the reflectance at the ground level. If you're trying to detect water, you want to know how much light the water reflected, not how much light ended up at the satellite. And once the light gets reflected, as it passes through the atmosphere, some of it gets scattered or absorbed, and the value would change. So what you're really after is the surface reflectance product. And that's the next level of processing, where you apply certain algorithms of what the atmospheric composition looked at that point of time. And then you take those values from the level 1 and correct them to what it would have been at the ground level. And this is what is known as the surface reflectance. And if for a given product or a sensor, if you have access to surface reflectance data, that will be the most accurate data, and you should definitely use that. And then there are level 3 products where you are not looking at the product as a different scenes as captured by the satellite, but they are transferred to a particular grid, and you get a uniform amount of scenes. So some of these products are distributed as part of a uniform grid, and you can say, I want a grid number this, regardless of which scene it was part of. So this is all quite abstract. Let's look at what these different processing levels do to your satellite image and how does it change your data. So earlier we looked at the Landsat data. This is an image of Landsat. And if you look at the raw data as it was captured by a satellite, and you query for a value and say, what does this pixel value mean in band number 5? And you would end up with this value like 13,381. Now, what does that mean? It doesn't mean anything, because that is just the amount of how bright that area looked in that particular band. So we need to convert this radiance values into a reflectance value, and that is more useful for that analysis. And that's what the level 1 processing does. If you look at the level 1 process data for this particular satellite, and you can look at the image, you look at the band value for the band 5, and you see a value like 0.23. And now that makes sense. The 0.23 is a reflectance value. That means the light that was for that particular wavelength that this band is in, 23% of it got reflected, rest of it got absorbed. And that is very useful in analysis. Now you know for each pixel how much light was reflected in that band, and then you can use that for your analysis. But remember, this is still TOA reflectance, that is as measured by the satellite after the light has passed through the atmosphere. So you apply the next level of correction, which is the level 2 processing, and you end up with an image like this. And you can see the value changes slightly. And this is the real value of the amount of light that got reflected at that particular pixel. And you can't really know the value because your sensor is up in the space, but you can know the composition of atmosphere at that point, and you can correct for it. And then you end up with this value, which is more useful. Next, we'll talk about image resolution. This is also an important concept in remote sensing, and you need to learn about that to really find the right data set for your application. There are many, many different kinds of resolution. Many times when people refer to resolution, they are talking about spatial resolution. And this is essentially, resolution is how effective is your sensor at separating objects. So in a spatial resolution means that how smaller objects can you detect from your sensor. And if your sensor is high resolution, that means you are able to detect very small objects. If your sensor is low resolution, you are able to detect only large objects. So for example, if your resolution of your satellite is 30 centimeters, that means each pixel is 30 centimeter by 30 centimeter wide, and any object larger than 30 centimeter would be more than one pixel, and you can detect that. If it's an object that is smaller than 30 centimeter, you can't tell it apart because you can only measure stuff that is at least 30 centimeter. And that is also referred as the pixel size of the data, or GSD. So when you look at some satellite specification, that would say this satellite has a GSD of 1 meter. That means each pixel in the satellite image refers to 1 meter on the ground. Another kind of resolution that is important is the temporal resolution. How frequently can the satellite capture the same area again? And if you're doing studies of an area, you need to kind of monitor the area. You need to know, when can I get an image of this area next? And this is also known as a revisit time. And there are satellites which have different revisit times, and we'll talk later more about that. Another kind of resolution is the spectral resolution. That means how many different bands you are capturing the data on. As you saw earlier, the Landsat satellite has 11 different bands. So now you're able to capture the information in so many different bands, versus if you look at some of the high resolution satellites, they'll be capturing data only in 3 or maybe 5 bands. So those have lower spectral resolutions versus the other sensors. The last one is something called a radiometric resolution. And that means how many different levels of brightness your satellite can measure. Remember, I showed you that pixel and the value was 13,386. Now, how many different levels of those values can the satellite detect? If the two pixels are almost the same, but they have slight variation in the reflectance, can your sensor detect that? And depending on the satellite type, it can detect many, many different levels of grayscale variations. And then that would allow you to see those objects and distinguish between them. This is also known as a bit depth. So let's look at all of these resolutions in detail. First up is the spatial resolution. We'll look at the data from a low resolution to high resolution and see how that matters. This is data from a satellite called SMAP, which is measuring soil moisture on the surface. The Earth's surface actually emits radio waves in the microwave spectrum, and this satellite detects those and tries to determine how much moisture does the soil contain. And this is very useful for, say, drought monitoring. This is a satellite that is capturing the image for a large region. So this is useful for large scale monitoring. If you look at each pixel, here each pixel is actually 30 kilometers wide. So if you zoomed in more, everything will be the same value, and you can't distinguish objects that are smaller than 30 kilometers. But this is useful for regional level monitoring. As you can see, if you overlay this on a state level, you can see which parts of the state have currently dry conditions, or they're experiencing anomalies in the soil moisture, and that is useful for a regional level tracking of drought. Going one level up, this is another data set called CHIRPS. And this is measuring precipitation from satellite and combining with the ground data to give you this data set, which is 6 kilometer in resolution. That means each pixel now is 6 kilometer wide. And that means you are now able to do a much more detailed analysis at, say, admin 2 level, a district level. You can see this pixel, you can see the variation in the rainfall of this data. Next level is this another data set called nighttime radiance. This is a very important data set for urban studies where you are able to measure the light that is reflected at night. So this is this sensor aboard the satellite called VIRS, which is very sensitive to low light. And this measures, it captures the data at night and looks at which parts of the world have lights. And this is very useful to track, say, rural electrification, urban growth, etc. And this data comes as a resolution of 750 meters. So remember, we went from a 30 kilometer resolution to 6 kilometer resolution to a 750 meter resolution. And this data is useful for, say, a city level monitoring, where you can see at a city level which suburbs have lights at night and how those are changing over time. Next level of resolution is this data set called MODIS. And MODIS is a really important sensor in remote sensing because it's able to capture the data, entire world's data every day at this fairly high resolution at 250 meters. So you're able to see the changes in the world at 250 meters on a daily basis. And this is a very important data set for doing any kind of Earth observation and Earth monitoring. And you can see this now, you're looking at, say, different wards in a city or different neighborhoods of the city. You can actually see some data. Zooming in further, we have Landsat 8 data, and the resolution of that is 30 meters. So one pixel in a Landsat 8 image refers to 30 meters on the ground. And now you can look at a neighborhood level and kind of identify different objects. Now you can see which is the urban area, which are the water, etc. And going one level up is the Sentinel-2 dataset, which is operated by European Space Agency. And this is a public domain dataset where each pixel is now 10-meter resolution. So now you are able to see much more detail. You can see how the images become sharp going from Landsat 8 to Sentinel-2. And Sentinel-2 is really useful dataset for any kind of urban studies. And this is the best resolution data that is available in the public domain. If you want to get even higher resolution data, maybe you're looking at Google Maps and saying, this base image looks so much sharper. I can actually see the individual cars or houses. Those are high resolution images that are with a pixel resolution of 50 centimeters or even lower. So those are often available as a commercial data, not as a public domain data. But if you are interested, you can purchase those and use them in your analysis. Another related aspect to your pixel size is something called a swath width. And this term might come up as you work with your remote sensing data set. And what this refers to is that how wide of a data that you can capture at a single go. So as the satellite's up in the space, it's capturing the data. How wide is that data it's capturing? And generally the swath widths and the pixel size are inversely related. If you want a higher resolution data, you are able to scan only a small portion. Versus if you scan a large portion at a time, you can do that, but your resolution, pixel resolution suffers and you get a lower resolution data. So the satellites typically have to compromise between these two. And you can see as you go from VIRS, which is the 750 meter data, to Sentinel-2, which is 10 meter data, the amount of data you can capture in a single pass changes, and that reduces as you move up the resolution. Next, let's talk about temporal resolution. There are different satellites that capture data at different frequencies. So for example, the satellite mission called GPM, which is measuring precipitation. And this satellite gives you one image every 3 hours. And this is very useful for, say, tracking storms and tracking your rainfall, because you need more real-time information. So every 3 hours, you get a new image and you can look at how much rainfall has happened in a particular area within the last 3 hours. MODIS, as I mentioned, you have MODIS is able to capture an image every day. This sensor is actually on board two different satellites. One is called Terra and one is called Aqua, and they are in different configurations. So now with the combination of these two satellites, you are able to look at each place in the world twice at 250-meter resolution. Landsat 8 has a 16-day temporal resolution. That means once an image is captured, the satellite comes back on to that place after 16 days. And this is useful, but again, if you want to monitor something regular, you need a more higher temporal resolution. One way to address this is to have more satellites, and that's what Sentinel-2 does, where each satellite has a revisit time of 10 days, but then you put two satellites in different orbits. So now with the combination of two satellites, you're able to get one image from either of the satellites every 5 days. And this is the approach that a lot of the modern satellite companies have taken, where they, instead of launching one satellite, they are launching a constellation of satellites. And that means you're able to monitor the data every day at a very high temporal resolution. Next, let's talk about the spectral resolution. And when we look at the remote sensing data, typically you get data captured in different bands of wavelength. And that is useful for analysis, as we see later on. Most of the data that you will be working with will be called multispectral. That means you have information in more than one band. And it could be multispectral data in just R, G, and B band, red, green, and blue, or it could be in other bands as we talked about, infrared and shortwave infrared and so on. Hyperspectral is another kind of remote sensing where you have hundreds of different bands. Instead of capturing this data in this wide band, you are capturing data in very narrow bands, but you have hundreds of them. And that kind of data is very useful in detecting a specific type of object, because then you can have a very accurate measurement of a particular species of tree, and you can know exactly what the reflectances are in these different narrow bands, and you can try to match them from the data that's captured by a satellite. The next one is the radiometric resolution. And we talked about this is the bit depth, how many levels of brightness can your sensor measure. And again, different satellites have different radiometric resolutions. If you look at the old Landsat satellites, and this were early in the 70s, and the technology wasn't that great, then they were able to take the data only in a 4-bit. That means they were able to measure the brightness in only 0 to 63. So if the light got completely absorbed, it would be 0, and all of the light got reflected, the value would be 63. So you can have only 64 levels of information in your data, and that means if there are two objects which are very similar, they would have a similar value, and you can't really tell them apart. As the technology got matured, you have data that is captured in a more number of bits. So you have Landsat 4 to 7 that were 8-bit data. Most of the modern satellites are 12 bits or higher. And that means you have many, many different levels of information that can be measured through that. So now you have this data. You have data with different spatial resolutions, spectral resolution, radiometric resolution, and you end up with this data. Now, how do you make sense of it? What can you do with it? So the first technique is just visual interpretation. Just look at the data and you can derive useful information out of it. So the first type of thing you can do is take the bands that are in the visible spectrum, red, green, and blue, put them together, and then you can see the world as it looks and as it's captured by the satellite. And this itself is quite useful. You can go to any place in the world and see how the world looks. And since the data is captured every 5 days or every 10 days, you can go and see how the world looked 5 days back, and you get this up-to-date information. You can see, visually what is happening there. You can actually humanize, and even computers can display this data only in these 3 channels, red, green, and blue. And those colors are combined to form a new color and be shown to us. So you have these 3 channels. So instead of putting, say, red band in the red channel, green band in the green channel, and blue band in the blue channel, if you have multispectral data, you can play around with the combination and generate an image that is, not a real image, but it can still highlight a certain kind of objects. So the most important combination is used is something called a false color infrared. And these are called composites. You can create a composite image like this. And in the remote sensing terminology, this is used as FCC, false color composite. And what this image is showing is that the infrared band, where the vegetation reflects a lot of infrared light, you put that in the red band, put the red band in the green channel, green band in the blue channel. And what comes out is this image, which looks red, but that shows really the healthy vegetation. So if you've got an image of, say, farmland, and you want to just look at which areas have healthy vegetation, if you just create this composite, you can immediately visually see which areas have healthy vegetation versus which are not vegetation. One useful thing you can do is, there are some areas which have, say, a green color looking grass, but that's not a real grass. So if you create a false color composite and look at that area will not be red, because that's though it might look green in an RGB composite, but when you actually create a false color composite, that it's because it's not a vegetation, it won't be highlighted as red. So those are the kind of nuances that you can really pick it up when you create this composite. There are many different composites. This is a composite where you can highlight the urban areas. And as I mentioned, the shortwave infrared is a light get reflected by the built-up areas. So in this case, if you're trying to map urban areas, you can create this composites there. This is another composite that is for detecting agriculture areas. And those are useful for creating, say, maps, or you're trying to map or detect areas visually. These are the kind of compositing technique you can use and display this data. Now moving from a more visual approach to a more analytical approach, where you're not only looking at it, but you have computers, you have algorithms, you can now detect stuff automatically through the satellite imagery. And that is a really exciting part of remote sensing. And most of the time, any application that you want to do, it will involve some kind of indexes or band ratios. And that's what we'll learn about now. So let's see how this band ratios work by looking at how they apply to an image. This is a Sentinel-2 image of the same area that we've been looking at. Let's say you want to extract all the areas that are vegetation. You want to compute what is the total area of vegetation in this particular image. How do you do that? As we learned, the vegetation has a very high reflectance in NIR band and very low reflectance in red band. So if you take a ratio of NIR and red band, so take the value in the NIR band divided by the value of the red band, the vegetation will have a very high value and rest of the features will have very low value. And then you can have a cutoff and say anything higher than this is a vegetation. And to do this, you can take a band ratio, or you can do even something better, which is normalizing. That means you take the ratio, but you first subtract the values and then divide it by the sum of it. And this is called a normalized difference. And what this does, it gives you a value in the range of -1 to 1. And that makes it easy. Depending on your sensor, you might have different ratios, but the normalized ratios would be always -1 to 1. And then you can say anything higher than a certain ratio is vegetation. And this is one of the most important indexes in remote sensing. It's called NDVI, Normalized Difference Vegetation Index. And this is nothing but a ratio of the near infrared and red band. And you can see, and when you do that, it highlights all the vegetation. And in this image, you may not be able to see there is a small island in this lake and there's some vegetation there. But if you take this ratio, you are clearly able to take this. And now you can say any pixel value in this NDVI is greater than 0.2 is vegetation. And you can just extract those pixels out, compute the total area out of that. Right? So this is how the indexes really help you analyze this data. Let's say you want to detect water. So coming back to our chart, the water can be effectively detected using this ratio of green and red bands. And you can see no other features has the similar pattern in those bands. So when you take a ratio of the green and red band, you end up a green and NIR band, you can actually end up with this index called NDWI. And because water absorbs a lot of the infrared light and reflects green light, you are able to just detect those pixels which have this high values in this ratio. And you can see from this image, if I give you this image, you may not be able to identify pixels visually, but if you just take this ratio, you can see all the surface water. So for surface water mapping, this is a really useful index called NDWI. Next one, let's see how we can detect urban areas. You can see the other two features we saw. They have lower values in shortwave infrared and higher values in other bands. But this one is different. So if we take the ratio of the shortwave infrared and the near infrared bands, and that would highlight the built-up areas. And this is known as a normalized difference built-up index, NDBI. And this shows you exactly what are the built-up areas. If you see here, this is the lake, and there's a jogging path around this lake. And if you look at this built-up area, you can see this is the concrete that is reflecting higher in the shortwave infrared band, and that shows up in the NDBI index. So we learned about different indexes. There are hundreds of them, and depending on an application, you'll have to find the suitable index and apply that to your data, and then that'll help you extract and detect the particular kind of feature that you're looking at. The last bit that I want to cover is that not all data has equal access. And depending on what you want to do, you might say, I want this data is ideal for my application, but there are some challenges that you may have to face depending on the data access. So the first type of data is something called a real-time or near real-time data. That means you are able to access this data very fast after it was captured. And this is typically the weather data that is made available very shortly, the data such as MODIS, which is again available within a few hours of capture. And this is very useful where you're trying to have a real-time application on the satellite data. As you kind of move towards more higher resolution data, they need to go through different processing chains, and that means there is a higher latency involved in getting access to this data. This real-time data, again, they do not get atmospheric corrections, or they do not get certain type of corrections, because they would just get this data, do the basic processing, make it available to the users for the real-time application. Most of the providers would then provide you with a standard product that is corrected, calibrated, and which is much more useful for scientific analysis. And again, there's a latency of many weeks or days before this product is available. And this is because the correction would depend on maybe some other data sets that have a latency, or maybe a human has to look at and validate this data before this is made available to the public. There is the third kind of latency, which is reprocess. That means right now, maybe the provider has one algorithm for doing, say, surface reflectance. And maybe there's more research and they find that there's a better way to process this data that is more accurate. And then they would make a reprocessed version of this data available at a later stage. So sometimes when you're searching for some data, you'll say, do you want a standard product or a reprocessed product? And then you now know what that means. The data access, as I mentioned, all the data that I've shown you today, be it the night lights data or the Sentinel-2 data, these are all public domain data. That means it's freely available to the public at no cost. And this is really important from scientific perspective, from usage perspective, where you are readily able to access this data through a platform like Google Earth Engine. There are certain data sets which are free, but after some time, because a lot of these applications, the most valuable applications are immediately after. Many people are willing to pay for data that is captured and made available in real time. So a lot of the providers would make this available at a cost, but the older data, after a few months, they would say, now you can just access this data for free. And that's kind of a dual pricing model that has, and the WIRS nighttime data has this model where after 3 months, you are able to access the data. So if you want to know what happened yesterday or last month, you may have to pay for this data, but if you want to do a time series analysis of last 5 years, you can take this data free of cost. Then there's commercial data that you don't get any data for free, but you get a license, you pay for it, you get a license for a specific use case or a specific imagery, and then you can access it through the data. And most of the high resolution data, which is sub-meter pixel resolution, those are available as a commercial data. Another important thing to know about the satellite is the value of the satellite data comes from the fact that many of the satellites have been capturing data for decades together. And that has formed this long-term historic record of the Earth's surface. And if you're studying a phenomena like land use change or global warming, these are the kind of phenomena that requires this long-term historic record. And that is something that's available now. So just as to show you this, this is data from Landsat, and Landsat has been capturing the data since 70s, and most of the data from 80s is now available. So now last 40 years, you are able to look at any place on Earth and see how that place has changed. And this is one of the lakes in Bangalore that is kind of dried up over time, and you can see over the years what has been the situation in this lake. And not only you can see this visually, but since this is remote sensing data with different bands, you can actually do analysis and extract stuff out of it. So the same area, now I'm looking at the NDWI band and NDWI ratio, and I can now look at how the surface water for this lake has changed over different time. And this is very useful when you are trying to track the amount of surface water over time. Maybe you are trying to tackle a water crisis and want to understand how different phenomena affect the surface water. This kind of a long-term historic record is really useful. So that's it from my side. That was quite a lengthy introduction to remote sensing, but I hope you get an idea of what remote sensing can do and what type of data is available. If you want to test your knowledge and just revise some of the concepts, I have a quiz for you. Do try out the quiz and let me know what you think. Thank you.